So we've already looked at Cartesian coordinates. In today's lecture, we are going to look at other coordinate systems. In 2D. Okay, so these are two-dimensional coordinate systems. One can generalize these into 3D, but I guess we will look at that later. So the two coordinate systems that we are going to look at are one, tangential normal coordinates, and two, polar coordinates. Okay, and these are both sort of 2D coordinate systems, as I mentioned here. Before we look at these two coordinate systems, let's first look at a special case of both 1 and 2. Which is motion in a circle, specifically some coordinate system for motion in a circle. And then we will generalize this, what we do here, into these two coordinate systems, which are going to be useful for more general motion. Okay. So what do we mean by motion in a circle? So let's say we have some circle. Oops. I suppose that's a circle, roughly. And we have the origin O. And let's say that's a radius r, and we have theta, this angle theta, and let's say we have point P, which is x comma y, and this point P goes in the circle. Okay, and I suppose we have the usual Cartesian coordinates. Okay, so how do we describe the motion of this point in a circle? First of all, of course, there's a relationship between r and theta and x and y. So what is the relationship? This is classic trigonometry. X is going to be r cosine theta, and y is going to be r sine theta, right? So okay. Of course, r is called radius. Theta, you might say, is the angular position. And then let's say the particle moves with angular rate theta dot equals omega. Okay, so the rate of change of theta is omega, or theta dot. Okay, so given all this, what is the speed with which the particle travels? Okay, so what is the speed? Speed v of the particle is given by r theta dot or r omega. Okay, and this is of course tangential to the circle. The velocity So why is the speed of the particle r omega or r theta dot? Can we provide a proof of that? Or can we get some intuition for that? Okay, here's the proof or intuition. Let me just sort of give you first a fact that you may all be familiar with already. So if you have an arc of a circle, let me actually draw. Let's say this is theta. This circumference of that arc is basically, and this is r, that's basically r theta, right? So, and if you have a full circle, then you have theta equals 2 pi and circumference equals 2 pi r, okay? So basically, the distance traveled by the particle when it subtends an angle theta at the center and the radius is r, the distance traveled along the circle is r theta. So we can use that. So if we have a small part of the circle and the small change in angle is d theta, this is still r. Let's say this distance traveled is ds. ds is going to be equal to r d theta, okay? Distance traveled. In time dt equals ds equals r d theta, where d theta is angle change in time dt. So what is speed? Equals distance over time and we just go ds over dt equals r d theta by dt. If you want to be a bit more rigorous, what you would do is rather than say ds here, you can say delta s, delta t, and so on. And then speed is approximately equal to delta theta by delta t, and then you take the limit of t going to 0, and you will get basically d theta by dt. Okay, so let me just throw that as an aside. Delta t, delta theta, delta s, and then v equals limit delta t going to 0, r delta theta by delta t, which is r d theta by dt. Okay, so that's just an aside. Okay, so this is an important relationship. This is an important relationship. V equals r d theta by dt, or v equals r theta dot. Okay. What's next? The next thing that we want to do is define coordinate systems. We're going to define a coordinate system that is, like we said, is a special case of both tangential normal and polar coordinates. We're going to use the notation of polar coordinates for now. So what's a coordinate system? So let's say we have some point here, and we can connect the point to the origin O, and then a unit vector along the radial direction we can call E sub r, and then the perpendicular to that is E theta, and E theta is defined usually in the direction theta increases. If theta increases this way, E theta is defined this way. Okay. So these are unit vectors. So ER is sometimes called the radial unit vector. E theta is sometimes called the azimuthal unit vector. Okay. Okay, so we've now defined unit vectors. Now let's actually convert these positions and velocities into vectors now in terms of these unit vectors. So, of course, we already know that the position vector r is OP. We can certainly write it in terms of Cartesian coordinates as we did in the previous lecture, xi plus yj. But can we write it in terms of these coordinates, these sort of polar coordinates, in terms of r, er, and so on? Okay, so the point P is basically equal to r, er. Okay, so it's r, that's the length of this vector OP, and then the direction of the vector is er. Okay, so that's r, er, and then the velocity v, we've already said its magnitude is r theta dot, and then its direction, we haven't explicitly stated it yet, but essentially I guess we stated it here. Its velocity is tangential to the circle, which makes sense. It's going to be in this direction. Okay, E theta. Okay, so r is the r er, v is r theta dot E theta. This actually suggests something we briefly touched upon last time. You can also get the velocity v as dr by dt. Okay, so by the way, let me just put blocks around these things. Oops, I guess the auto boxing function misfired there. Okay, so those two are important equations. And the third equation is note v is also equal to dr by dt because it's the rate of change of position. This is the position vector. This is velocity. And when we ask for velocity, remember to always give a vector answer. And when we ask for speed, you can give us a scalar answer. Okay. You want to be sure that what we are asking is a vector, and if you are, then give us a vector answer. And unless we specify the coordinate system, you can provide the answer in Cartesian coordinates or some other coordinates. Okay. Okay, so v is dr by dt, rate of change of position vector, which is basically d by dt of r er, which is r der by dt because r is just a constant. But we already know that this quantity equals, let's call this 1, let's call this 2. This is basically equal to r theta dot E theta from 2. So sort of equating these two things, we get r der by dt equals r theta dot d E theta by dt. You can cancel the r's, which basically says that der by dt equals theta dot E d E theta sorry, not d theta, e theta. Okay. So the rate of change of ER is theta dot e theta. Previously, in the previous lecture, we looked at rate of change of I and j was equal to 0. Here, this unit vector, even though its magnitude is constant, its direction constantly changes as the point moves around in the circle. So this is not a constant vector. And because its direction changes, it's got a derivative that's not equal to 0, and that derivative, it turns out, is equal to theta dot e theta. Okay. The rate of change of ER is in the e theta direction, because if this point is here and then if this point moves here, the new ER vector is going to be here. The difference between the old ER vector and the new ER vector is going to be roughly in that direction, which is e theta. Okay. That's why it's along the e theta direction, and then by how much ER changes is proportional to how fast P is moving around. Okay. So here's an example where the rate of change of a vector is not equal to 0. A unit vector is not equal to 0. You can check d e theta by dt equals minus theta dot er. Okay, so when e theta changes by a little bit, if you have a new point here, e theta will change. The rate of change is going to be in the ER direction, but it's going to be inwards, but it changes by the same amount, I guess, in terms of numerical value. Okay, so we're not going to prove that. I'm just going to state it. These two equations are more important than these equations. These equations are just for your general information, but these two equations are important. Okay, so that's motion in a circle. We can represent it by essentially what are called polar coordinates. So these coordinates are called polar coordinates. But this is the special case. Okay, we can do one more differentiation, look at what the acceleration is. Acceleration A is just dv by dt, which is d by dt of r theta dot e theta. Now we can use chain rule or product rule, whatever you want to call it. Let's bring r outside. We have theta dot e theta. Both theta dot and e theta can change in time. So although r is a constant, these two other variables can change in time. So we have r, derivative of theta dot is theta double dot, and then e theta, plus we have r theta dot d by dt of e theta. So this is product rule or chain rule. So chain rule is a general term that refers to all these things as special cases. Okay, so we already saw that what the derivative of d theta by dt is, d theta by dt is, and that's this thing, so we can plug that in there. So it's minus theta dot er. So sort of rearranging, we have r theta dot square er plus r theta double dot e theta. So this is the acceleration of a point P. Okay, so let me just rewrite it here. A equals minus r theta dot square er plus r theta double dot e theta. Okay, is this formula familiar to all of you? You may have seen some version of this at some point. The two terms have physical interpretation or have special names. Okay, so this term is along ER, and specifically it's along minus ER. In other words, it's an acceleration term along the direction joining the point toward the center. So it's an acceleration toward the center of the circle. And because it's an acceleration term toward the center of the circle, it's called the centripetal acceleration. And this term, I guess, is would be called the tangential acceleration because it's or azimuthal acceleration because it's acceleration along e theta. Okay, tangent to the circle or along the e theta direction, which is sometimes called the azimuthal direction. Okay, what is the physical significance of these two terms? You have velocity. The velocity is only along the tangent to the circle, right? Because it's moving in a circle, the velocity is only along the tangent to the circle. The speed may change. The speed of the particle may change. And basically this term has to do with how the velocity, the speed changes, right? So this is basically d by dt of r theta dot. That's basically dv dot or dv by dt. And that, so this acceleration, let me just write it down here. Acceleration due to speed v namely the velocity magnitude changing. And then this term has to do with acceleration due to the direction of v changing. Okay, so v is a vector. It's got two components, two parts, so to speak, the magnitude and the direction. This term has to do with how the magnitude of the velocity changes, and this term has to do with how the direction of the velocity changes, right? So this is the velocity direction, and it sort of keeps changing, and it's changing at momentarily in the direction that is toward the center of the object, okay? And that's called centripetal acceleration and then tangential acceleration for this term. Any questions about this? So that's motion in a circle, more or less. What we shall do next is generalize these formulas. So there's a formula for the position vector, the formula for velocity, there's a formula for acceleration. We're now going to talk about tangential normal coordinates and polar coordinates when things are not moving in a circle, but things are moving in a more complicated sort of way, okay? So that's